Hello everyone. In this video tutorial, I am going to explain how we can solve moment of inertia problem. To solve any moment of inertia problem, we require basic formulas. So I will explain some of the important formula required for solving problem. So for example, if I consider a rectangle of size with the width b and depth d, the area is given by b into d, where x bar distance is b by 2 and y bar distance is d by 2, and moment of inertia about xx reference axis or centroidal axis is bdq by 12, and yy centroidal axis, that is dbq by 12. So if I consider a triangle of width b and height d, the area is given by half into bd and x bar is given by b by 2 and y bar is given by d by 3, and moment of inertia about xx centroidal axis is given by bdq by 36, and about yy centroidal axis is given by dbq by 36. Then if I consider a circle of radius r, then area of the circle I can call it as pi r square, and x bar distance, that is r, and y bar distance I can say it is r. Then moment of inertia about horizontal centroidal axis, that is Ixx, is pi r to the power 4 divided by 4, and about yy axis, that is pi r to the power 4 divided by 4. If I consider a semicircle of radius r, then area is given by pi r square divided by 2, and x bar distance is r, and y bar distance is given by 4r by 3 pi. Then if you want moment of inertia about horizontal centroidal axis, that is 0.11 r to the power 4, and about vertical centroidal axis, that is pi r to the power 4 divided by 8. Then if I consider a quarter circle of radius r, then area is pi r square divided by 4. Then x bar distance, that we can get by using formula 4r by 3 pi, and y bar distance we can obtain by using the formula 4r by 3 pi, and Ixx, moment of inertia about horizontal centroidal axis, it is 0.055 r to the power 4, and vertical centroidal axis, that is 0.055 r to the power 4. So these are the basic formula. So all the derivations we've done, including centroid and moment of inertia, in the previous videos. You can refer that. Then one more thing I want to recall. So that is parallel axis theorem. So if I consider one rectangle, for example, so we know that this is the horizontal centroidal axis. I will take one reference axis here, that is AB. So now distance between reference axis and centroidal axis, I can call it as y bar, since it is in vertical direction, y bar. So therefore, moment of inertia about AB reference axis is given by moment of inertia of the centroidal axis plus total area into distance between that reference axis and centroidal axis whole square. So this is the parallel axis theorem. So similarly, for example, if I take CD reference axis, then we know that vertical centroidal axis I can call it as YY. So as per the parallel axis theorem, if I want ICD, I can obtain by IYY plus A into distance between reference axis and centroidal axis, I can call it as X bar. So therefore X bar whole square. So if you understand this parallel axis theorem, we can solve any problem in the moment of inertia concept. So here I divided that entire set of moment of inertia problem into two types. So first one is problem related to moment of inertia about centroidal axis. So they will ask us to find the moment of inertia about centroidal axis. In the second part, I'm going to explain problem related to moment of inertia about given reference axis. So the difference is in the centroidal axis problem, about centroidal axis problem, we have to find the centroidal axis, we have to locate x bar and y bar. Then about that particular axis, we have to find moment of inertia. But in the second type of problem, so they will give the reference axis directly. We have to find moment of inertia about that particular axis. So in the first type of problem, there are two part. In the second type of problem, directly we are calculating moment of inertia. So let us see the first problem. Determine the moment of inertia of the unequal section shown in the figure about its centroidal axis. So if you see this particular figure, we can say that this figure is symmetric about y-axis. Okay, so this is symmetric about y-axis. So directly I can take y axis here, but I don't know where is our x axis. This is not symmetric about x centroidal axis. So to locate that, I have to find the y bar distance. So in the solution part, x bar no need to locate because it is symmetric about y axis, but y bar I have to find it. We know that y bar is nothing but sigma a into y divided by sigma a. So I want to find different areas, then uh, I can locate the centroid. For that I will divide this entire figure into known components. So I will call this as first component, then this rectangle as the second component, that whatever the web portion, and bottom flange I will call it as third component. So now area of the first component, so I will call it as A1. I can calculate, that is B into D, 200 into 10. I can say that 2000 millimeter square. Similarly, I can calculate what is A2. So that is nothing but 300 into 10. So that is 3000 millimeter square. So if I come to the bottom flange, again I can call it as A3. So that is 300 into 10. So that is again 3000 millimeter square. So to find the y bar value, I need some reference axis. So I will take this as my reference axis. We have seen in the centroidal location of the centroid problems. So we need some reference axis. I will call this as AB reference axis. With respect to that, I'm going to find what is the y bar distance. So therefore, first for the first figure, so I will call the centroid of the first figure is somewhere here. So from the reference axis, this is the y1 distance. So from the reference axis, this is the y1 distance. So if you want y1 distance, that is nothing but 10 mm plus 300 mm plus, so the last figure, that is 10 by 2, I can say that 5 mm. So totally it is 315 mm. Okay, so if I want to find the y2 value, so how we can calculate y2? So for that, that is the distance to the centroid of the second figure. So if you see in the problem, that is somewhere here. So I can say that this is the y2 distance. So from the reference axis to this centroid of the second figure, I can say that this is y2 distance. So to find y2, I can say that it is 10 mm, 10 mm plus 10 mm plus half of 300 mm. So that is d by 2. So that is nothing but 150. Therefore, 150. So totally it is 160 mm. So that is the y2 value. So the third thing I want the distance to the centroid of the third component. So directly I can say that y3 is nothing but 10 divided by 2. So that is 5 mm. So once I get the value of a and y, now easily I can calculate what is the centroid. Okay, so that is y bar. So to find y bar, this is nothing but a1 into x y1, a1 x y1 plus a2 y2 plus a3 y3 divided by a1 plus a2 plus a3. So this is the formula. So I'm going to substitute all the values here. So I found it is 2000 into 315 plus 3000 into 160 plus 3000 into 5 mm. So entire value is divided by, so total area sigma A I can calculate here, that is nothing but 8000 mm square. So I will substitute here, that is 8000 mm square. So if you do the calculation, I will get the answer. So I'm going to get, that is 140.625 millimeter. So after getting this value, I'm going to locate the horizontal centroidal axis. So we got 140.625. I know that our y2 value is 160. You can see here y2 value is 160. So therefore we got 140.625. So I'm going to locate just below the 160. So our value I'm going to locate here. So our centroidal axis at a distance of y bar. So we know that y bar we got 140.625. So once I get the centroidal axis xx, so now the things are very easy. So our CG is somewhere here. Okay, I can call it as G. So therefore, if I want to find moment of inertia about horizontal centroidal axis, Ixx is given by parallel axis theorem. It is sigma Ixx plus a into y square. So this is our formula. See, we have three components. So let us take one by one. So therefore, Ixx is equal to, so the first component is the rectangle, top rectangle. We know that for the rectangle, the Ixx value is BDQ by 12. So if I consider the top rectangle, the B value, the first rectangle, B value is 200 mm. So therefore, BDQ by 12, that is 200 into, so for the first rectangle, D value is 10 mm. Therefore, 10 cube divided by 12. So we already calculated what is the area. It is nothing but 2000 mm square. So I'm going to substitute here 2000 mm square. Then y distance. So now we should be very careful. That is the distance from the centroid of the first figure to the reference axis. So now reference axis is x-x axis. So for the calculation of centroid, we take an AB as a reference axis. But I'm as per the parallel axis theorem, I'm calculating moment of inertia about x-x axis now. So therefore, horizontal centroidal axis is the reference axis. Therefore, I want this particular distance. So if you want to find uh, this particular distance, so if I want to find this distance, so I can say that it is nothing but 315 minus 140.625. Okay, so that is the actual distance. So that is the 315 minus 140.625. That is the centroid of the distance from the centroid of the first figure to the reference axis. So x-axis is the reference axis. So that is the particular distance. So if I come to the second component, so again it is rectangle. So we know that moment of inertia about centroidal axis, that is bdq by 12. So we'll add that one. So therefore b for the second figure, that is 10 mm, into d value for the second figure, that is 300 mm, 300 mm. So therefore 300 cube divided by 12 plus area of the second figure, we know that that is 3000, we already calculated a2, into now the distance from the center of the second figure to the reference axis. So I want this particular distance. So to find that, it is nothing but 160 minus 140.625. So if I do that, I will get this particular distance. So therefore that is 160 minus 140.625 whole square. So again we have third figure, so I will add that one. So for the third figure, if you come to that particular figure, so b value is 300, b value is 300 into d value is 10 mm, bd cube by 12, plus area of the third figure we already calculated, that is 3000 mm square, into now the distance I wanted is, that is the distance from the centroid of the third figure, that is somewhere here, to the x-axis reference axis. So if you want to find this particular distance, that I can say that there is nothing but 140.625 minus 5 whole square. So that is the particular distance. So if I do this calculation, I'm going to get Ixx is equal to, so the answer you are going to get is 139.663 into 10 to the power 6 millimeter to the power 4. So let us calculate about Iyy. So if you want Iyy, so that is nothing but sigma Iyy plus a into x square. So let us consider one by one. So if I consider the first figure, so that is db cube by 12. For the first figure, d is 10 mm and b is 200 mm. D is 10 mm and B is 200 mm. So therefore dB cube by 12, 10 into 200 cube divided by 12 plus area of the first figure, so that is 2000. So but if you see that the x distance, that is the distance from the centroid of the first figure to the yy reference axis or yy centroidal axis, that is 0. So it is coinciding each other. So therefore second term will become 0. So I will move on to the second figure. Again db cube divided by 12. For the second figure, d value is 300, b value, that is 10 cube divided by 12 plus area is 3000. Again, if you see that the centroid of the second figure is coinciding with y axis, that is our reference axis. So therefore, again second term, in the second term, that will become 0. So therefore, if you come to the third figure, plus again db cube by 12, d is 10 mm, b is 300 mm cube divided by 12, plus area is 3000 into, again it is coinciding, whatever the centroid of the third figure is coinciding with y reference axis, therefore that is also will become 0. So if you do the calculation, we are going to get 2.9192 into 10 to the power 7 millimeter to the power 4, or else you can write 29.192 into 10 to the power 6, 29.192 into 10 to the power 6 millimeter to the power 4. So let us discuss the second problem. So they ask, calculate the least radius of gyration for the section shown in the figure. So before starting with this particular problem, let us see what is least radius of gyration. So radius of gyration is given by I is equal to a into k square. So k is the radius of gyration. Therefore, k is equal to I divided by a. So if I take the root, I will get the radius of gyration. So but they, in this particular problem, they asked least radius of gyration. So least means whatever the I value I'm going to get least. So I have to find I value, ixx and iyy. So whichever is least, for that I have to calculate radius of gyration. So to do that, I can say that it is, we have to find the moment of inertia about centroidal axis. So therefore, first step we have to locate the centroid. So for that I have to use the formula x bar is equal to sigma a into x divided by sigma a, and one more formula, y bar is equal to sigma a into y divided by sigma a. So for that reason, I will divide this particular figure into three rectangular components. So I will call this as first rectangular component, and vertical web, I will call it as second rectangular component, and this particular horizontal flange, bottom flange, I'll call it as third rectangular component. So let us calculate different areas. So therefore, A1 is given by 120 into 10, so that is 1200 millimeters square. Then if I see that A2, so we have to get the net depth of this particular section. So we have seen the overall depth is 120. So therefore net depth is 100 mm. So I have to deduct 10 mm here and 10 mm here from the 120. So therefore net depth is 100 mm. So therefore 100 into width of that section is 12. Again I'm going to get 1200 mm square. So width of this section is 12 mm, so therefore 1200 mm square. So if you come to the third figure, so I will call it as A3. So that is 180 into thickness of that particular section, that is 10 mm. So therefore 1800 mm square. So to locate the centroid, first we want reference axis. So at the bottom, I will take this as reference axis. I can call it as OX reference axis, and vertically I'm going to take OY reference axis. So therefore, x1 distance or y1 distance I have to calculate. So let us say what is x1 distance. So x1 distance is distance from OY reference axis to the centroid of the first figure. So I can say that this is the distance, that is x1 distance. So if you want to find that particular distance, So that is nothing but 120 divided by 2. So overall it is 120. So divided by 2 will give x1 distance. So therefore 120 divided by 2, that is 60 mm is the x1 distance. So x2 distance. So that is the distance from OY reference axis to the centroid of the second figure. So that is, I can say that this is the distance. So centroid of the second figure is somewhere here. So I can say that this is x2 distance. So if you want to find x2 distance, so that is nothing but 12 divided by 2. So that is nothing but 12 divided by 2. So I will say that x2 is equal to 12 divided by 2. So that is 6 mm. Okay, so I want x3 distance, that is the distance from OY reference axis to the centroid of the third component. So overall width is 180 mm, therefore 180 divided by 2, I can say that 90 mm. So I calculated x1, x2 and x3. Similarly, I have to calculate what is y1, y2 and y3. So to find y1, y2 and y3, so y1 distance is the distance to the centroid of the first component. So I can say that this is the y1 distance. So to find that, y1 is nothing but 10 mm plus 100 mm. So I know that this is 100 mm, 100 mm. So plus 10 by 2. So I will say, I will repeat. So that is 10 mm plus 100 mm plus to the center of the third figure, that is somewhere here. I can say that this is 10 divided by 2. So therefore 10 plus 100 plus 10 divided by 2, so that is 115 m. So similarly, I'm going to calculate what is y2. So that is the distance from OX reference axis to the centroid of the second figure. I can say that this is the distance, so y2. So therefore, that is nothing but 10 mm plus 100 divided by 2. So 10 mm plus 100 divided by 2, I can say that 60 mm. So now finally we want to y3. So y3 directly I can say that y3 is equal to 10 divided by 2, that is 5 m. So I calculated what is a1, a2, a3, x1, x2 and x3. So now easily I can calculate what is x bar and y bar. So I'm going to do that now. So first initially I'm going to take x bar. We know the formula, sigma a into x divided by sigma a. So therefore a1 x1 plus a2 x2 plus a3 x3 divided by sigma a, or a1 plus a2 plus a3. So let us see what is sigma a here. So that is the summation of all the areas. So if you do that, sigma a I'm going to get, that is 4200 mm. So that is 1200, 1200 and 1800. So which is nothing but 4200 mm. So therefore I'm going to substitute all the values here. So therefore x bar is equal to a1 is 1200 into x1 is 60 plus a2 is 1200 into x2 is 60 mm, sorry 6 mm, 6 mm plus a3 is 1800 into 90 mm divided by overall area, that is 4200 mm. So I'm going to get x bar value is 57.429 millimeter. So that is the x bar. Similarly, I am going to calculate y bar. So y bar is nothing but a1 y1, a2 y2, a3 y3 divided by sigma. So we did all the calculation of area and y distances. Just substitute, that is 1200 into y1 we got 115 plus a2 I got 1200 into y2 I got 60 plus 1800 into 90. So that is a3 y3. So divided by total area we got 4200. So if you do the calculation, we are going to get that is 52.143 millimeter. So these are the x bar and y bar. So the main thing in the previous problem, the given figure is symmetric about y axis, so we calculated only y bar value. Okay, so but in this case it is not symmetric about x-axis as well as y-axis. So I calculated both the values x bar as well as y bar. So once I get the answer, let us locate the centroidal axis. So therefore, the centroidal axis, the horizontal centroidal axis at a distance of y bar, that is 52.143. So I know that y2 is 60 mm. You can see here that is 60 mm. So I got 52.143. So therefore that is just below that y2 value. So that is somewhere here. Okay, so I'm going to locate that one. So horizontal x axis or centroidal axis here. So at a distance of y bar is equal to 52.143 millimeter. So again, vertical centroidal axis, that is y axis at a distance of x bar, we know that that is 57.429. So you can see here, this is at a distance of 60 mm, x1 is at a distance of 60 mm. I got 57.429. So therefore just before that we are going to get vertical centroidal axis. I'm going to locate here just before the centroid or it, from the x bar. So therefore I'm going to locate like this. So I will call it as y centroidal axis. So therefore I can get the value of CG over here. So that is at a distance of x bar is equal to 57.429 millimeter. So these are the values. So now let us calculate Ixx and Iyy. So once I get the Ixx and Iyy, I can compare which is the smaller value. For that I can calculate what is the radius of gyration. So uh, therefore I know that Ixx is nothing but summation of Ixx plus, so I will take this as capital X because about centroidal axis. So this is about individual component. I'll take small xx, then area into y square. Okay, so let us see one by one. For the first figure, that is rectangle, B value is 120 and D value is 10 mm. So therefore, I can say that that is B is 120 and D value is 10 mm. Therefore, BD cube by 12 plus area of the first figure we already calculated, that is 1200 into the distance. What I want is that is the distance from the centroid of the first figure to the reference axis. I'm calculating about x axis. So how we can calculate is, that is x1 minus y bar. So if I want this particular distance, I can say that that is not x1, that is y1 minus y bar. So y1 we already know, that is 115. So therefore 115 minus y bar is 52.143. So that value whole square. So if I come to the second figure, again it is rectangle. So therefore again it is addition, therefore plus. So for the second figure, B value is 12 mm. You can observe that width of that second section is 12 mm into depth of that section. Net depth is 100 mm. We have seen already. Therefore 12 into 100 cube divided by 12 plus area we calculated, that is 1200. Now I want the distance. So that is the distance from the centroid of the second figure to the centroidal axis or reference axis. So therefore I want this distance. So that is nothing but y2 minus y bar. So therefore y2 we already calculated, that is 60 mm. Y bar is 52.143. So that value whole square. So again if I come back to the third figure, so place in the third figure, that is rectangle, therefore BD is 180 BDQ. So D is 10 mm, BDQ by 12 plus area of the third figure, we know that there is 1800 mm. So A3 value is 1800 mm. So now I want the distance from centroid of the third figure to the XX reference axis, because I'm calculating moment of inertia about XX reference axis. So therefore that distance is given by y bar minus y1. If you observe in the figure, that is given by y bar. Y bar is 52.143 minus y1. Y1, not y1, y3. So that is y3 is 5 mm. So that value whole square. So if you do the calculation, I will get the value of Ixx. So after calculation, we are going to get the value, that is 9.840 into 10 to the power 6 millimeter to the power 4. So that is the one value. So I want to calculate Iyy. So I can say that Iyy is nothing but sigma Iyy plus a into x square. So I will take this as capital. So Iyy is equal to sigma Iyy plus a into x square. So therefore a will start one by one. For the first figure, that is dbq by 12. So d is 10 mm and b is 12 mm. So therefore 10 into 120 cube divided by 12 db cube by 12 plus area, we know that that is 1200 a1 into, now I want the distance from the centroid of the first figure to the yy reference axis. I want this particular distance. So I can say that that is the distance is nothing but x bar minus, or x1 minus x bar. So x1 we know that 60, x1 minus x bar, that is 57.429 whole square. So that is for the first figure. So if I come back to the second figure, again dbq by 12. For the second figure, d value is 100 mm. We have seen that is net depth is 100 mm. So therefore 100 into b value is 12 mm, dbq divided by 12 okay, dv cube by 12 plus area of the second figure, that is again 1200 mm, 1200 mm. So now I want the distance from centroid of the second figure to the OY reference axis. So I want this particular distance. To do that calculation, I can say that that is nothing but into, so that is nothing but y bar minus x2. So y bar minus x. So the second term is, that is 1200 area into distance from the centroid of the second figure to the YY reference axis. So I can say that that is nothing but x bar minus x2. So x bar we got 57.429, x2 we got 6 mm. So therefore 6 whole square, that is the second term. If I go to the third component, so b value is 180, so it is db cube by 12, therefore 10 into 180 cube divided by 12, area is 1800 a3. So now I want the distance from the centroid of the third figure to YY reference axis. I can say that this is the distance. So I can calculate, that is x3 minus y bar. So x3 we know that that is 90 mm, 90 mm minus x bar is 57.429 whole square. So if you do this calculation, I'm going to get Iyy is equal to 11.0 11.4058 into 10 to the power 6 millimeter to the power 4. So the problem is not over. They ask the radius of gyration. So if I want to get the minimum radius of gyration, I have to use minimum Iyy value. So if you compare Ixx and Iyy, Ixx value is the minimum value. Therefore, minimum radius of gyration is given by Ixx. Therefore, I will call it as Kxx is equal to root of Ixx divided by sigma A or A. So sigma A already we calculated. So therefore Kxx is equal to root of 9.840 into 10 to the power 6 divided by sigma A. So that is, we already calculated, that is 4200. So therefore we'll get the minimum radius of gyration is 48.403 millimeter. So this is the second problem. So the third problem I'm going to discuss, the calculate the moment of inertia of the shaded area for the following figure with respect to the centroidal x-axis. So we have to find the moment of inertia about centroidal axis, that is xx centroidal axis. So therefore they asked only about centroidal xx axis, so no need to find x bar, only we have to find y bar. So let us locate the centroid first. So that is, we know that in the solution part, if I want to locate xx axis, I have to find what is y bar. So therefore sigma a into y divided by sigma A. So for that, let us divide this entire area into number of components. So this area I can divide into three known components. So the first one, I will take the triangle. The second area I am going to take the rectangle. The third area I am going to take the semicircle. So therefore area of the first figure, that is triangle, I can say that half into base into height. So therefore half into base of the triangle we can see from the figure, that is 100 mm. Then height of the triangle is 30 mm. So I will get area of this particular figure, that is 1500 mm square. So the second area, so I will take that rectangle A2 is equal to B into D. So therefore 100 into 70, not 75, 55 mm, 30 plus 25. So I can say that 5500 mm square. So the third figure, that is semicircle. So therefore A3 is equal to pi r square divided by 2. So pi into radius is 25, diameter is 50. So therefore area we are going to get, that is 981.74 millimeter square. 981.74 millimeter square. So once I get the area, so I can find what is y bar. So before that I want to find what is y1, y2 and y3. So if I want to find y1, this is the distance to the centroid of the first component from OX reference axis. So therefore, if you want to find that particular distance, I can say that it is nothing but 25 plus 30 plus 1/3 of 30. So therefore, 25 plus 30, we know that for triangle it is at a distance of 1/3 of height. So I can say that this distance is 65 mm. So y2 distance, it is the distance to the centroid of the second figure from OX reference axis. I can say that this is y2, this is y1. So that is y2, directly I can say that is nothing but 55 divided by 2. So overall height is 55 divided by 2, that is 27.5 millimeter. So for the third figure, the centroid is somewhere here. I can say that this is at a distance of 4r divided by 3 pi. So therefore 4r divided by 3 pi is equal to 4 into r is 25 divided by 3 into pi. So therefore the value we are going to get is 10.61 mm. 4r divided by 3 pi. So once I get these values, easily I can find it what is y bar. So therefore y bar is equal to a1 into y1. So a1 is 1500, y1 is 65. So a2 into y2, that is 5500 into y2 is 27.5. Now we should be very careful. If you see that whatever the semicircle portion, that is the opening, so therefore we have to deduct that particular value. So if any area is overlapping another area, that means it is opening. So that whatever the semicircle is overlapping our rectangle, so I can say that that is opening. Therefore minus area of the semicircle, that is 981.74, that is y3 is 10.61. So overall divided by entire area. So therefore entire area is 1500 plus 5500 minus 981.74. Here also you should be very careful while doing the summation of the area. Also we have to deduct that particular area. So after that, if you do the calculation, we are going to get So the value we are going to get, that is 39.601 millimeter. So once I get the centroidal axis, we can locate here. So we can see in the figure, so this is at a distance of 25 mm. So therefore I want 39.6, so therefore I can locate somewhere here. So that is the x horizontal axis. So no need to locate CG because I am not calculating x bar value. So I calculated only y bar value. So y bar we got 39.601. So therefore let us calculate Ixx. So to find the Ixx, I can take the formula sigma Ixx plus a into y square. So let us take one by one. So the first figure is triangle. So we know that for the triangle Ixx is BDQ by 36. So for this particular triangle B is 100, D is 30, BDQ divided by 36. Area of the triangle we already calculated, that is 1500. So now y distance, that is the distance from the centroid of the first figure to the reference axis. So reference axis is x-axis. So therefore I want this particular distance. So if you want to find that particular distance, I can say that it is nothing but y1 minus y bar. So y1 we know that that is 65 minus y bar is 39.601 whole square. So that is the first term. So plus the second value, so that is the rectangle. So for rectangle Ixx is BDQ by 12. So therefore B for the rectangle is 100, D is 55, BD cube divided by 12. Area of the rectangle is 5500. So now the distance. So distance is nothing but it is the distance from the centroid of the rectangle to the x reference axis. So I want this particular distance. So to find that, I can say that it is y bar minus y2 whole square. So y bar we got 39.601, y2 we know that that is 27.5 whole square. So the last figure I know that that is opening, so therefore I have to deduct that one. So for the semicircle, as per our derivation, you can see that if this is the derivation, you can refer the video also. Ixx I got 0.11 r to the power 4. So Iyy I got 5r to the power 4 divided by 8. So I want here Ixx, that is 0.11 r to the power 4. So therefore 0.11 r value is 25, therefore r to the power 4 plus area. So area we got 981.74 into distance I want. So the distance is nothing but it is from the centroid of the third figure, centroid of the circle to the reference axis. So I want this particular distance. So I can calculate it as y bar, that is 39.601 minus y3. So y3 we calculated it as 10.61. So this value whole square. So if you do the calculation, we are going to get. So the answer you are going to get, that is 2.366 into 10 to the power 6 millimeter to the power 4. So same thing they asked, find the moment of inertia about horizontal centroidal axis, that is Ixx is equal to 2.366 into 10 to the power 6 millimeter to the power 4. So this is the fourth problem in moment of inertia. So as I said, this is the second type of problem in which the moment of inertia is asked about reference axis. So let us see the problem. Determine the moment of inertia about x axis where all the dimensions are in millimeter. So they mentioned x axis, but they not mentioned it as x centroidal axis. So that means they given already given one reference axis, that is x axis here. So either they may give it as AB reference axis or PQ reference axis, whatever it is. But about that reference axis, we have to find the moment of inertia. So therefore, comparatively previous problems, it is very easy because no need to calculate centroidal axis. Okay. So directly I can start with the solution here. I will take this as whatever the rectangle as component 1 and triangle as component 2, and whatever the circle, I will take this as component 3. Okay, so after taking these things, so I will calculate what is uh, A1, A2 and A3. So therefore A1, that is rectangle, so easily I can calculate, that is 100 into 150, so that is 15,000 millimeters square. Then A2, so A2 is a triangle, I can say that half into base into height. Okay, so for the rectangle, that is B into D, so directly I can take, so but for the triangle it is half into base into height. So if you see in the figure, that is half into base is 100 mm and height is 120 mm. So we are going to get 6000 mm square. So the third figure, that is circle, I will call it as A3. So for the circle we know that area is pi r square. So therefore pi into 25 square, we are going to get 1963.49 millimeter square. So these are the three areas what we got here. So next, directly I will take the moment of inertia formula. So I want to calculate about x reference axis. Therefore sigma ix plus a into y square. So now let us see first figure, that is rectangle. So therefore Ix is BD cube by 12. So therefore 100 into B is the 100 and D is, so this is B 100. Then D is 150. 150 cube divided by 12. So that is the first term, plus area of the rectangle we already calculated, that is 15,000. So now the question is, what is y value? So that is the distance from the centroid of the rectangle, that is somewhere here, to the reference axis. So now reference axis is xx. So therefore this is y1. So directly I can say that that is 75 whole square. Okay. So we'll come to the second one. So the moment of inertia of the triangle is given by BD cube by 36. So if you see that the B value of the triangle is 100, so this is the distance, and the D value for the triangle, that is 120 cube divided by 36. Then we know that the area of the triangle, that is 6000, we already calculated in the previous step. So therefore 6000. So now I want the distance from the reference axis, that is x axis, to the centroid of the triangle. So we did the derivation, and we also know that we have, if I have a triangle of height d, from this particular base, the centroid of the triangle is at a distance of d by 3. Similarly, in this case, the depth of the triangle is 120. So that is 120 divided by 3 whole square. So that is the second term. So we have third figure. that is the circle, so that is the opening, so that therefore I'm going to deduct. So the thing is, if any shape is going to overlap, so I can say that if you try to draw this particular uh, diagram in 3D, it is something like this. So whatever that circle is opening, so that is overlapping the rectangle, that means I can say that it is opening. So therefore, the moment of inertia of the circle. So therefore, for the third figure, I can say that that is minus pi r to the power 4, that is ixx value. So the r value is 25 r to the power 4 divided by 4 plus area of the circle, that is 1963 into 49. So now the distance is, I can say that this is the y3 distance. So this is previously we taken this as d3, that is y2 distance. So now y3 distance directly I can say that that is 75. So therefore 75 square. So after doing this calculation, we are going to get the value is 1.155 into 10 to the power 8 millimeter to the power 4. So this is the final answer.